Okay, so there was a huge glitch, but I think we are back. Okay, so hopefully you are tuned in. All right. And again, I am going to start going through this presentation, covering some key information that you should definitely know for the exam. Okay, so let's get to it. So can you list 5 important lab safety rules? Again, this is something that you should just be able to identify. And occasionally it's a written question, like what's another safety precaution that should be followed? So for example, wearing appropriate PPE, so goggles, gloves, lab apron, whatever might be appropriate for the lab. Following directions means only doing what has been assigned, not doing some side experiment just because you're curious. No food, no drink in the lab, tying your hair back, no open-toed shoes, no horseplay. So if you're asked to identify an additional lab safety rule, these are good ones to kind of go by. All right, can you identify common lab tools? And again, typically you're not going to be asked, what is the name of this lab equipment? But you might see pictures of lab equipment in questions or them in a reading. Okay, so beakers and the tongs used to pick up beakers, a graduated cylinder to measure volume, flasks and scupulas. Okay, so you can see this equipment. This is just the major equipment that you might see in a question or see mentioned in a question. Okay. Can you identify variables? All right, so the difference between a dependent and an independent variable. So the independent variable is the thing I'm changing. For example, I might change the temperature of the water to see what happens. And then the dependent variable is what is the effect of what I did. So remember, I changed the temperature of the water, so how much sugar dissolves or how quickly does it dissolve? That would be the dependent variable. Okay, so the independent variable I am changing, and the dependent variable depends on what I change. So what happened because of what I did? Can you identify significant figures? Okay, so again, to identify significant figures, you are going to see if there's a decimal point. If there is a decimal point, you are going to begin counting from this side of the number, and you're going to look for the first digit that is not a 0. Ding, ding, ding. And then you are going to start counting. So that is 1 significant figure, 2. Okay. So every time there is a decimal point, you start from this side of the number and do the same thing. Not a 0, so I start here. So then everything counts. Okay. If there is no decimal point, you do the opposite, but literally follow the same rule. Okay. So this is a 0, skip it. 0, skip it. Okay. So this is the first not 0. So that one would only have 1. Okay. So again, we call this the Atlantic Pacific rule, meaning when the decimal is absent, we begin counting from the right side of the number, like the Atlantic Ocean. When the decimal is present, we begin counting from the left side of the number, like the Pacific Ocean. The decimal is present. Okay. And then here are the answers for these significant figures. Hopefully you have an understanding of what those are. Okay. If not, go back, pause it, try them yourself, see if you can get them. All right. Can you add and subtract with significant figures? Okay. So here's a math problem. Can you figure out how many significant figures are supposed to be in your answer? Well, the rule for addition and subtraction is that the answer has to have the same number of decimal places, that the least number of digits after the decimal. So you can see this one has 2 digits after the decimal. This one has 1 digit after the decimal. So my answer should have only 1 digit after the decimal. Okay, so that is the answer, 3.63, but rounded to the correct number of significant figures, it would be 3.6. Okay. For multiplying and dividing, the rule is that you need the least number of significant figures. So this is 3 significant figures. This is 2 significant figures, right? So my answer, the first one is what you get when you put it in the calculator. The second one is rounded to the correct number of significant figures, all right? All right, so reading a graduated cylinder, remember this shape right here is called the meniscus. You should read from the bottom of the meniscus, and your eyeball, right, should be right here. So reading at this level. So you shouldn't be reading from looking up above or down below. It should be literally right across. And we should always be estimating. Okay, so if this is 12 and this is 13, that means I can estimate one digit between them. Okay, so 12 point something, since it's between 12 and 13. So you kind of have to estimate. Well, it's more than halfway, so I might say, for example, 12.8 milliliters. Okay, so we always have to estimate one additional decimal place. Putting numbers into scientific notation. All right, you should be able to do that. So we need to move the decimal right here. Why? Because we need this digit immediately to the left of the decimal to be a number that is between 1 and 9. It can't be 0. And then the decimal, if it's not written, is all the way over here. So we have to move the decimal all those places, count how many digits, and add that as the exponent. If it was a big number like this one, the exponent will be positive. If it was a small number like this one, you can see the exponent will be negative. You're going to do the opposite when you take it out of scientific notation. Okay, so you're going to write those digits for 3, right? That's the digits that I have. And then here was the decimal, and I need to move it -6. So I need to move it 6 places, but I need to make the number smaller, right? So based on what the exponent is, negative or positive, you're either making a larger or a smaller number. So in this case, we'd be moving the decimal over to make a small number, and we moved it 6 places. And then on the calculator, I'm going to kind of quickly go through this, but this is just depending on the calculator that you have. If you want to put a number into scientific notation using this calculator, you can switch to Sci mode. Now, I put a note here because the downside is all numbers will then be reported in scientific notation. If you don't want that, don't use this, okay? Norm is just normal, where if it needs to use scientific notation, like the number's too big, it will. But scientific notation puts everything into scientific notation. Okay. On the other hand, you can use on this calculator times 10 to the n key to put something into scientific notation, and this GIF kind of runs through the process. Some calculators use EE as the method. Just one thing that I will make a note of is, in order to use the negative exponent, make sure that you are not using the minus sign. It will definitely say like system error or something. So you need to use the negative that is in parentheses, and right here it's under the number 3. So make sure that you are doing that if you want the negative exponent in the calculator. Okay, but again, if you want to go back through it, this GIF will kind of take you through it. You can just write it out on paper, take it out of scientific notation. But if you want to use the calculator, this is how you could do it. All right, so basically the only conversions that I have seen asked on the exam is being able to convert between kilo and milli, or between milli and like a base unit. So know this conversion factor, 1,000 grams in a kilogram, so that you can do this conversion. And know that for a milli, it's 1,000 milliliters, okay? Can you define the 2 types of substances? Okay, so the reason I'm starting with this particular topic is, of all of the topics, physical behavior of matter is the one that is tested the most on the exam, okay? The rest are kind of a little hard to predict, but they really love the content from this section, physical behavior of matter. It covers a wide range of things, so I'm starting here. So the 2 types of substances you should be able to define are elements and compounds. What should you know? Elements cannot be broken down by chemical means, and compounds can. Compounds are combined in a fixed ratio. So what does that mean? That means the formula is always the same. So if it is H2O, that is water, If it is a molecule of water, it will always have the atoms in that fixed ratio. If it is hydrogen peroxide, the formula will be H2O2, and the molecule will always have that same exact formula, always. Okay, so can you draw a particle diagram of an element? Here are two options. So we're going to have one type of atom. And even when it's diatomic, you can see it's two of the same atom bonded together. So that's still an element because it's one kind of atom. So an element only has one kind of atom. And remember, that means it has the same number of protons in its nucleus, because that's how we're going to define an element. It has the same number of protons. Oh, I'm so sorry that is being laggy. All right, I could try and cut off this camera and I could try and hide the camera and see if that helps. So I'll try that and hide the camera, and you let me know if it helps, okay? Okay, so I'm still gonna talk, but the camera's hidden, so see if it helps, okay? So again, an element has the same number of protons, okay? Oops, hold on. All right, let me come back over here. Okay, so can you draw a particle diagram for a compound? So a compound, remember, has two or more types of elements bonded together, and they're in a fixed ratio. So you can see this example right here has one of this type of atom bonded to one of this type of atom, whereas this compound has two of this type of atom bonded to this atom. Okay. All right. So so I'm just going to say here, let me know if it's better without the camera. If not, I'll put the camera back on, but I just want to test it out and see. So again, a compound is going to have a unique formula like this, like this. Okay, so those elements are going to be bonded together, okay? Can you identify the diatomic elements? You literally have to know these. So you have to know which elements exist as diatomic, meaning they have one atom of an element bonded to another atom of the same exact elements. And the phrase that I teach my students is BrINCIHOF. So that means bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine on the periodic table. Those specific 7 elements are diatomic, okay? And hydrogen is alone right here, but then you can see it's this little section right here. So you can kind of remember where it is on the periodic table. Okay, that may help, but BrINCIHOF definitely will let you know which elements are diatomic. Can you define allotropes? All right, so allotropes, do you remember? They are different forms of the same element. So they have different structure and different properties. The two that are tested, the most common are carbon and oxygen. So carbon exists as many allotropes, but the two most common would be diamond and graphite. And obviously they have different properties. And why do they have different properties? Because they have different structures. And oxygen gas and ozone, O2 versus O3. And they have different structures, so they have different properties. Anytime there is a different structure, you will have different properties. Okay, so now I kind of turn the camera back on so we can kind of see if there is any difference. Okay. So the ones that I kind of went through for diatomic, those are the specific elements. So if I go back here, so these elements are always diatomic. And I should say that this right here, where we have noble gases, those will be monatomic, meaning they will exist as single elements. Okay, but yes, there are just specific certain elements that will be diatomic. Okay. All right, so it helps. So I'm going to turn that camera back off. Okay, so we will just leave it off and we'll do it with this, and I will just keep talking. Okay. Yes, you do absolutely have to remember the diatomic elements. All right, so there's nowhere on the reference table that you can find it. So yes, remember them. Okay. All right, so can you define the two types of mixtures? Okay, so the thing is, matter is either a substance or a mixture. If it is a substance, it is an element or a compound. Okay, if it is a mixture, it is these two types, which would be homogeneous or heterogeneous. Now, homogeneous means that the components, well, any type of mixture, the components are physically combined. And if it is homogeneous, the particles are distributed evenly. If it is heterogeneous, the particles are not distributed evenly. Okay. Now, I put a little note here to remember that the proportions and properties in a mixture can vary. So you could have something that has more salt. If it's salt water, for example, they could have more salt. It would be saltier, right? So the properties are different. So in a mixture, the proportions and properties can vary. And can you determine when to use distillation to physically separate a mixture? Well, when you distill something, you're going to boil it, okay? And you're going to boil it to a certain temperature. And what's going to happen is some of the liquid is going to evaporate, then will condense, and you will end up separating the two liquids based on their boiling point. So we have two liquids combined, and we separate them based on their differences in boiling point. Okay, so that's when you use distillation. All right, so let's look at another way to separate a mixture. And why do we talk about these? Because mixtures are the only things that can be physically separated. Compounds can be chemically separated. Mixtures can be physically separated. Okay. When do you use evaporation to physically separate a mixture? Well, this is when you have something that is dissolved. So you have salt dissolved in water and you want to separate that mixture after. Then if you evaporate the water, okay, then you are left with that solid solute remaining. Okay, so evaporation will get rid of the solvent and leave the solute. Can you determine when to use filtration? Well, filtration is when you have something that hasn't dissolved. So you have sand and water. So we can separate sand from water by using filtration. On the filter paper will be stuck the undissolved solute, and going through will be the solvent, but also anything that is dissolved in the solvent. So think about when you make coffee, what comes through the filter is coffee flavored water, coffee colored water, right? But the coffee grounds stay stuck in the filter. So it's important to remember that what is dissolved in the solvent passes through the filter paper. Okay, so that is definitely something that has been tested multiple ways on the exam. So for sure, remember that. Okay. Can you determine when to use chromatography? Also, they love to test this one for physical separation. So this is a lab technique that's used to separate a mixture into colors, and it's based on differences in particle size. So that means big particles kind of get stuck down here at the bottom, okay? And little particles are more able to move up the paper. Also, solubility. So if this is water and this ink is soluble, meaning it dissolves in water, then it tends to move up the paper with the water, okay? And then the last one would be based on polarity. And polarity depending what the paper is and what the solvent is. So if the dye or the certain colors in the ink are have the same polarity, as the water, they tend to move with the water. Okay, so that's different ways that we can use chromatography. You should be able to draw a particle diagram of a homogeneous mixture or identify one. So like this, where you have two different substances, but they are evenly distributed. Okay. If you're doing a heterogeneous mixture, you're going to have at least two different substances, but they are not distributed evenly. Okay. You should be able to classify properties as physical or chemical. Okay, so remember, physical properties, I'm just literally describing something. I don't have to try to change it. Where if it's a chemical property, I'm going to have to try to change the substance in order to figure out if it has that property. So looking at these blue, that's just physical. I'm just looking at it. It's blue. It's reacting with oxygen, chemical. Okay. Okay, so I see your question. Yes, you definitely, absolutely need to know about intermolecular forces. Hydrogen bonding, you should know by name, okay? And the others, you should just know that they're there. Sometimes you will see van der Waals mentioned or London dispersion mentioned, but they will not expect you to kind of know the difference between them. You do have to be able to recognize the strength of the intermolecular forces, though. Okay, so knowing that hydrogen bonding is the strongest of that category of van der Waals is the category. Hydrogen bonding would be the strongest between hydrogen and then nitrogen, oxygen, and fluorine in a different molecule. Okay, and then the remaining van der Waals would be weaker. So London dispersion and dipole. Again, you may see them mentioned, but know hydrogen bonding by name for sure, and know that the strength of intermolecular forces has different effects. Like stronger intermolecular forces means higher boiling point. Love to test that one. Okay. And again, here just doing physical and chemical properties, and then the difference between physical and chemical changes. Again, this is relatively simple, it seems, but again, this category is really what they do focus on, the physical behavior of matter on the exam. So chemical changes, important thing is that you get a new substance, okay? So if I have H2, right, plus O2 yields H2O, just from the equation, I can tell different substance. It doesn't look exactly like this, right? So that's how I can tell it's chemical. You should be able to draw a physical change or identify it. It's just mixed around. The substances are exactly the same. Versus a chemical change, which is kind of what I was saying, what I just drew, is you see this and this on this side and something new, a new compound, a new arrangement of atoms on the other side. Okay, you should be able to define potential and kinetic energy. Literally all energy on the planet is either kinetic or potential. Kinetic is energy of motion and potential is stored energy. Okay, now most of the time we may be talking about chemical energy. That is the energy that is stored in bonds, but it is still potential. So all energy, either kinetic or potential. Potential is stored and kinetic has to do with movement. Okay. You should be able to define temperature. Literally, they love this. Again, if I was like, oh, what kind of question are they going to ask? Bam, this one right here, temperature. It's somewhere on the exam. So temperature is the average kinetic energy of the substance. So a question could be, which of the following has the highest kinetic energy? And you're just looking for the highest temperature. You don't care about anything else. All right, so definitely know how to define temperature. Can you define heat? Yes, you should be able to do this. So heat is energy that moves between two substances due to a difference in their temperature. And it always moves from warmer to colder. And the heat will stop moving when the temperatures are the same. So if this one was 100, right? And this one was 60, right? You can see the heat flow is going to be this way because 100 is the higher temperature. And then the heat flow will stop when the temperature is between these two temperatures, okay? All right, can you define exothermic and endothermic? All right, exothermic energy is released. If you're touching the reaction, it's going to feel warm because it's releasing heat. If it's endothermic, energy is absorbed. And if you're touching the reaction, it's going to feel cold because it's taking in energy from the atmosphere. You can use table I to identify reactions as exothermic or endothermic. Negative are exo and positive are endo, okay? You should know enthalpy and entropy. Now, they use the word enthalpy less often. Instead, they just typically use energy, but they could throw in enthalpy, all right? Enthalpy is basically total amount of energy, all the kinetic and all the potential energy. And then entropy is randomness or disorder, okay? So you should be able to draw particle diagrams for the states of matter. That's relatively simple. For solid, it should be at the bottom, all close, connected to each other. For a liquid, those particles are going to be further apart, and gas the furthest apart. Pay attention. Most of the time when they have you do this, they're going to tell you to draw 5 particles, or at least 5 particles. So just make sure you watch the language in the question. Can you compare the states of matter in terms of shape and volume? So you should know this, that solids have fixed or definite both shape and volume. Liquids have a variable shape, so they take the shape of their container, but their volume is fixed. And a gas has variable both shape and volume, so it fills up the entire container and takes the shape of the container. You should be able to compare them in terms of motion and intermolecular forces. So here's a little bit tied to intermolecular forces here, where you should know them in relationship to the states of matter. So in a solid, the particles are simply vibrating. In a liquid, the particles slide past each other. And a gas, they're just moving quickly. And solids have the strongest intermolecular forces because their particles are the closest together. And then in a gas, we have the weakest intermolecular forces because their particles are the furthest apart. All right, you should be able to compare the states of matter in terms of kinetic and potential energy. So if you think about a heating curve, for example, which we will get to, or a cooling curve, the gas at the top has the most potential and the most kinetic energy. And at the bottom, the solid has the least potential and the least kinetic. So this is kinetic energy. So while a sample of matter is just a solid, it is gaining kinetic energy as it's heated. And when something is melting, it is gaining potential energy. And when something is just a liquid being heated, it is going to gain kinetic energy. When it's boiling, gaining potential, and when it is just a gas being heated, it is gaining kinetic. Okay, so that visual hopefully helps you. Definitely, we're going to look at heating curves again, but you should definitely remember that. You should be able to compare the entropy of the states of matter. So that means gases have the most entropy and solids have the least. Now, aqueous solutions, AQ, have more entropy than a pure liquid because they have more than one substance in them, okay? So if you have a reaction and it's asking you for which one has the most entropy, look for gases, okay? If you're trying to find which one has the least entropy, look for solids, okay? What happens in these endothermic phase changes? So I like to show for my students if we have solid to liquid to gas, and we can go back and forth between them, right? When we go across this way, so think about when you melt something, you have to add energy in. So those are endothermic changes going that way, and going this way are exo. Okay, so you definitely should kind of have that in your head and know it. So for these, melting or fusion is solid to liquid. Vaporization, evaporation, liquid to gas, and sublimation, I'll tell you, sublimation starts with the letter S, so it is solid to gas. There's my little trick. I don't know, they love to ask sublimation. So if something sublimes, it started as a solid. Something goes through sublimation, it started as a solid, okay? And went to a gas. All right, now these are exothermic. This is the opposite. So freezing could be called solidification, and it's liquid to solid, condensation, gas to liquid, and then deposition, which is the opposite of sublimation. They ask this one less, but as soon as I say that, they'll ask it. But that is gas straight to solid. Okay. Now, on a heating curve, you should be able to identify the melting point. Okay. Now, if it tells you that it began as a solid, that helps. But if you see the whole curve like this, all of the pieces, then you know it started as a solid. The melting point is going to be the temperature where it is that first flat line. Okay, so in this case, that would be 1500 degrees Celsius. Boiling point is going to be the second flat line. Okay, and so I would go across from here, and that's again in between 2500 and 3000. Now, something you should notice, we'll get to it later, but this is melting, right? And this is boiling, okay? This is solid, this is liquid, and this is gas. You should definitely be able to identify all of the components on a heating or a cooling curve. You should be able to identify the sections where potential energy changes, okay? Potential energy changes means the temperature is constant. Why? Because temperature is kinetic energy. So it's going to be these two sections. That's where potential energy is changing. And in a heating curve, the potential energy goes up. In a cooling curve, the potential energy would go down. Okay? Where is kinetic energy changing? Well, remember, temperature is average kinetic energy. So the kinetic energy is changing where the temperature is changing. So it's all of those sections. And in a heating curve, kinetic energy is going up, and potential energy or kinetic energy in a cooling curve would be going down because temperature. So kinetic, temperature, potential, temperature is staying the same. So that's when potential can change. Can you identify the freezing point of water? Just got to know it. 273 Kelvin or 0 degrees Celsius. Okay. Can you identify the melting point of water? Well, it is literally the same as the freezing point. So 0 degrees Celsius or 273 Kelvin. Can you identify the condensation point of water? Well, that is 373 Kelvin or 100 degrees Celsius. I'm so glad that this is helpful. That's awesome. So thank you. And the boiling point of water, literally the same exact thing. Oops, so this is, there's a typo here. This is 373 Kelvin or 100 degrees Celsius. Okay, so 373 or 100 degrees Celsius. It is the same as the condensation point. So this one right here. Boiling point and condensation point are going to be the same. What about room temperature? So you have to have an understanding of what room temperature is. Room temperature is somewhere between 20 and 25 degrees Celsius. And the reason is sometimes you're asked to describe the heat flow of something based on room temperature. Yes, I am going to post this live later, okay? But to identify room temperature, just have an understanding of will heat flow to or from the air, okay? So for sure, you should know that it's somewhere in that range. And it doesn't really matter where in that range as long as you know it's somewhere in that vicinity, okay? All right, can you define specific heat capacity? All right, well, specific heat It's the amount of heat needed to raise the temperature of 1 gram by 1 degree Celsius. Now, in reality, you're not going to have to define it, but you should have an understanding. So when something has a small specific heat, it doesn't take a lot of heat for it to get warm. So when you use that for pots and pans, that makes sense. It is easy to warm up. It gets hot fast. And if the specific heat is greater, it's harder to warm up, but it is also going to retain its heat. So water has a relatively high specific heat, so it's a little bit harder for it to warm up, but it retains its heat. Hence, literally, we exist here on this planet, so thank goodness. Can you define heat of fusion? Okay, so heat of fusion is the amount of heat needed to melt 1 gram at its melting point. Okay, and it is listed on the reference table for water on table B. You do not have to memorize it for anything else. It must be given to you or you can calculate it. Okay, and the heat of fusion, the amount of heat needed to melt 1 gram at its melting point. The heat of vaporization, I thought it was on the wrong slide for a second. The amount of heat needed to vaporize 1 gram at its boiling point. Okay, so water has a relatively high specific heat, high heat of fusion and heat of vaporization. So if we look here, remember heat of fusion was right here. And this is heat of vaporization. And you can tell by this longer line that the heat of vaporization, like this, is larger than the heat of fusion. So that means it's going to take more heat, more energy for something to vaporize than it will for it to melt. Or when heat increases, I see your question. So when heat increases in terms of what? So heat is really like moving energy, like from high temperature to low temperature. Do you mean like when it is exothermic versus endothermic? Let me know and I'll try and answer your question. Okay, so heat of vaporization and heat of fusion for water are listed in table B again. For any other substance, you are not expected to memorize it. It will either be given to you in the question or you could calculate it from other information. Okay. You should know how to use the heat formula. Again, here is table B that I have been talking about with the constants for water. Okay, so, all right, so to identify whether something is exothermic or endothermic, I'll try to answer your question. You can do this. So first, let me finish going through this question. Maybe it'll help a little bit. So here we have a question. Here I see a temperature change, which is why I know I need the formula with a temperature change. I would set up the formula like this. And for temperature change, we're always going to do final temperature minus the initial temperature. If you do it that way, it will give you the answer if something is exothermic versus endothermic. Okay, so I'll show you what I mean. I set it up like this, which this is the final, this is the initial, right? So then I'm going to get negative 50. Okay, so when I do this math, I'm going to get this. And what you should know is that a negative Q value, a negative heat value, means that the change in heat was exothermic. It was being released. Okay, and then endothermic is going to be a positive value, meaning it is absorbed. Okay, so, well, this, we'll see how far I get. This unit is kind of long, but I'm going to try to get as far as I can, probably getting into atomic theory as well, and then I'll try to cover more than, again, on Thursday when I have a longer review session. Okay, so all right, so to answer your question between exothermic and endothermic, okay, so how do you know? First, one way right here is that it has a negative Q value, negative heat, right? That would indicate exothermic. If I wasn't calculating it, I would look at table I, and table I lists either a negative or a positive to indicate if it's exothermic or endothermic. How else could I identify it as exo versus endo? So if I had reactants and products, so whatever they are, and if I had heat on this side, so the product side, right? That is exothermic, right? And then if I had heat or energy or joules or calories or in some way listed with the reactants, that would be endothermic. Why? Because energy coming in with the reactants means endothermic. Energy coming out with the products means exothermic. Okay. I hope that helps. If it doesn't, ask a follow-up question, but hopefully that kind of clarifies a little bit. You should know when to use this heat formula, which is the heat of vaporization formula when we're talking about vaporizing or boiling point. Okay. And if it's water, we're simply using the value from table B. If it is not water, you have to be given the heat of vaporization, or you have to be given the heat, so then you can calculate the heat of vaporization. Okay. And then the same for heat of fusion, but we are talking about either melting or freezing. And we are using for water the values from table B. And if we are talking about other substances, you would have to be given the heat of fusion to do the calculation, or you could be given heat and asked to find heat of fusion. All right, so the 5 parts of the kinetic molecular theory. All right, so this is a lot, but it talks about gases. Okay, so particles, gas particles are really tiny, so tiny that we call their volume negligible. This word right here, Regents loves this word, negligible. Love it, love to use it. So the volume is negligible. The particles are moving in constant, random, straight line motion. Okay. The elastic collisions, they have elastic collisions with the walls of the container. And that means that no energy is lost or gained during any type of collision. So the total amount of energy inside the sample remains the same 100% of the time. In addition, that collisions results in gas pressure, which we'll address again in a little bit. Gas particles have no intermolecular forces. Now, in reality, we know that's not true, but this is the theory, right? And the average kinetic energy is directly proportional to the temperature. So that means if we're talking about kinetic energy and temperature, they're like this. So when kinetic energy goes up, the temperature goes up. Okay, so this is the kinetic molecular theory, right? It's important for understanding ideal gases versus real gases, okay? So what causes gas pressure? I kind of mentioned that, but that's collisions of the gas particles with the walls of the container. So bang, into the wall, gas pressure. More collisions, more pressure. More forceful collisions, more pressure. So can you define an ideal gas? All right. Well, an ideal gas is any gas that follows all parts of the kinetic molecular theory. In reality, no gases are ideal, but some get really close. So an ideal gas has no volume, but in reality, a real gas has volume. Okay, an ideal gas has no molecular attractions, but a real gas has some, because that's that intermolecular forces, right? And all substances have some type of intermolecular forces, right? And those are those van der Waals forces. So even tiny nonpolar molecules have some very weak London dispersion forces, okay? And an ideal gas follows all parts of the kinetic molecular theory at all pressures and all temperatures all the time, 100%. But in reality, real gases behave differently at different temperatures and pressures, okay? So can you identify the 2 most ideal gases? All right, so if I want to talk about what gases would be most ideal, I would need a gas that has low pressure and high temperature, okay? But if I'm talking about individual gases, when are they most ideal? Well, they're tiny. Why? Because kinetic molecular theory says that gases are, when they're ideal, have no volume. So if I'm talking about gases that have low volume, then they would be the most ideal. So that would be the two smallest gases on the periodic table, hydrogen and helium. They're tiny in comparison to ones like iodine, argon, krypton. Also, I would want them to be non-polar, okay? So that applies to hydrogen, right? Because although hydrogen is diatomic, it is one hydrogen bonded to one hydrogen, which means the bond is non-polar, and non-polar molecules have lower intermolecular forces. So if you're trying to pick which of the following is most ideal, pick the smallest or pick the non-polar one. Okay. And then when they're most ideal, which is kind of what I already said, is high temperature. Why? Because the particles have to be moving fast. And low pressure. Why? Because there's more space between the molecules. So I need more space in order for them to be more ideal. All right, for gases, can you state the relationship between temperature and pressure? Well, when temperature increases, pressure increases. Why? Because those collisions, remember, pressure results from collisions, and when temperature increases, kinetic energy increases. That means the particles are moving faster. When they're moving faster, they're going to collide more and with more energy. Okay? For gases, can you state the relationship between temperature and volume? Okay. Well, as temperature increases, the volume increases. Okay, so as temperature increases, the particles start moving faster and they're going to take up more space. So temperature increases, volume increases. Okay. And then what about the relationship between pressure and volume? Okay. So this one is pressure and volume are inversely related. So that means when we increase pressure, we decrease volume. When we decrease pressure, we increase volume. So if you remember this one, okay, the other gas relationships are direct. They look like this. This one for gases is the only one that looks like this, where it is an inverse relationship. So as volume increases, pressure is going to decrease. For volume and temperature, and for pressure and temperature, they look like this. Okay, so these are all pieces that tie into the combined gas law. And you may see Boyle's law or Charles' law or Gay-Lussac's law mentioned, but you don't have to recognize them by name, but you should know the relationships. Okay. Can you state Avogadro's law? Well, Avogadro's law says that if you have gases that are at the same temperature and the same pressure, they will have the same number of particles when they have the same volume. Okay, so you can see right here, we have same temperature, same pressure, right? Same temperature, same pressure, and we have the same number of molecules. So here, if I change the volume, so here, if I triple the volume, so see the volume here, right? And see the volume here. You can see that the pressure and the temperature are identical in both situations. That means if this is X number of particles, this is 3X, triple, okay? So they ask this question a lot. So which gas has the same number of particles? You're going to look for one that has the same volume. When they're at the same temperature and the same pressure, if they have the same volume, they have the same number of particles, okay? Can you define vapor pressure and boiling point? So vapor pressure, think about it. Vapor, gas. Pressure, literally pressure. So it's the pressure of the vapor, of the gas, in a closed system. Remember, we need a closed system in order to have equilibrium, all right? And then boiling point is a temperature, but it's when the vapor pressure equals the air or atmospheric pressure. So you can see that the differences in vapor pressure, right? So as you increase temperature, vapor pressure increases. This is going to be more pressure from that vapor, right? And you can see that if we're in the same situation, the atmospheric pressure isn't changing. and then eventually they will be equal. And at that point, we say it's boiling, okay? So what pressure do we need for normal boiling point? Well, that is standard pressure, okay? Standard pressure, 1 atmosphere or 101.3 kilopascals. That's listed in Table A. It means normal boiling point. Table H, okay, is one that lists vapor pressure for 4 liquids, and understanding that the normal boiling point is going to cross the line at standard pressure, okay? The relationship between atmospheric pressure and boiling point. So when atmospheric pressure increases, the boiling point increases. So when we go to the top of Mount Everest, which has a very high elevation, the atmospheric pressure is very low, so the boiling point is much lower. And when we talk about something that is like at a lower elevation, like the Dead Sea, for example, which is actually below sea level, then this boiling point is going to increase because it has more atmospheric pressure. So up high, there's less air pressure or atmospheric pressure. And down low, there is more air pressure or atmospheric pressure. So things are going to boil much faster with the same amount of heat applied at the top of a mountain versus at the bottom. All right,